Okay, once again, good morning. So at this time, we will talk about the exponential growth law and the exponential decay law. It actually the topic of the calculus 3. So actually, this topic is actually the application for the separable differential equation. Okay, so this topic actually has a mathematical model wherein we will have to derive from this given function, no, or equation. We will have to derive the mathematical model that can be used to solve for the exponential growth law and the exponential decay law. So, using the concept on the separable differential equation. Okay, let's begin with this one. So, let us have to derive. Actually, this time, we will have our goal is we will group between dy and y and dt and k. K is referring to any constant in the function. Okay, so we have here, we can actually multiply both sides by 1 over y. Okay, so we have here dy over dt. We can actually multiply both sides by 1 over y. Both sides. And that is equivalent to e times y times 1 over y. Okay, so this will be 1 over y, okay, 1 over y, dy over dt. Okay, that is actually equivalent to, kung makancel out ni, ang nag-play is only k, because k times 1 is k. Then after that, we can now still derive this one, or solve this one. We can multiply dt to the other side, so that we could have 1 over y, dy is equal to we have here k times dt. Okay? K times dt. So now they are being separated. So we can now integrate both sides of this equation. So we can have integral of 1 over y dy is equal to integral of k times dt. Next, integral of 1 over y is actually ln of y. Okay, that is equivalent to k times integral of integral of dt. Then, after that, we have here ln of y, okay, is equal to k times integral of dt is t, so plus c. So our goal is to find the solution for y. So we can have now y of t is equivalent to e to the power of k times t plus c. Then from that one, we can actually derive this given function as equivalent to y of t is equal to e to the power of c multiplied by a to the power of kt. No? They're just the same. This one are just the same. Then all we have to do, we can let t equivalent to 0 so that we can identify the initial value now of y when t is equal to 0. So at this time, we have here y of 0 is equal to, we have here e to the power of c times e to the power of k times 0. Then, simplify again, we get y of 0 is equivalent to e to the power of c times e to the power of 0. A times 0 is 0. After that, y of 0 now is equivalent to e to the power of c times 1. Because a number to the power of 0 is equivalent to 1 except 0. So at this time, we can now have y to the power of y of 0 is equal to e to the power of c. Wherein, we can now use this given. Okay, we can now use this one. Okay, so that we can rewrite, or instead of rewriting, no? Instead of rewriting what? This one. Okay, instead of rewriting e to the power of c, we can rewrite now y of 0 as our initial value for y. So therefore, y of t now is actually equivalent to what? Okay, y of t is equal to, we have e to the power of c which is y of 0. Okay, y of 0 is is equal to, or multiplied by a to the power of a times a. So this will be, okay, this will be the mathematical model that we're going to apply particularly in solving the exponential growth law and exponential decay law. So I will give you also an example about this one so that we can now utilize this given formula. Okay, so let us continue with example. This is now the sample problem for the exponential growth law and the exponential decay. No? So this is the application for the exponential separable differential equation. Okay, we have here an example. Consider a colony of bacteria that is observed to grow at a rate that is proportional to the number of cells per cell. At the start, there are 8,000 cells, meaning at the beginning, no, the initial value. After 2 hours, it increased to 14,000. How many will there be after 1 day if the growth rate is constant? Okay, so let us now figure out what are the given. First, we have here the initial value, which is y0, which is equivalent to, accordingly, at the start, we have 8,000. Okay, 8,000 cells. So from that, we can now write the equation y of t is equal to 8,000 a to the power of k times t. So this will be our mathematical model that can be, or that would help us to solve this entire problem. Okay. Another one, we are also given that y of 2, okay, when t is equal to 2, meaning after 2 hours, okay, 2 hours, okay, so at this time, when t is equal to 2 hours, okay, so when t is equal to 2 hours, we're also given that y of 2 is equal to, okay, when t is equal to 2 hours, it increased to 14,000, okay, cells. So 14,000 now, okay. So what we want to find out now is we'll have to solve first for the value of the constant at this time. So from that, from this given function, we can actually write as our use our equivalent values. We can have 14,000, okay, 14,000 is equivalent to 8,000 e to the power of k times t, which is 2 hours. Okay, when t is equal to 2, yep, 14,000. So we can now divide both sides by 8,000. So we can make 14,000 divided by 8,000 is equal to a to the power of 2k. Then to solve for this one, we know that a to the power of 2k is actually equivalent to 1.75. So at this time, we can now solve for the value of 2k. So we have here, 2k now is actually equivalent to ln. ln of 1.75. Okay? Or k is equivalent to ln of 1.75 over 2. Which is approximately equivalent to k is equivalent to what? 0.2798. You can actually use your calculator to generate a value which is equivalent to this one. 0.2798. Okay? So this will be our constant, no? When the cells will increase. So after that, we will solve now for the number of cells in 1 day. Okay, remember that 1 day is equivalent to 24 hours. Right? Okay? 1 day is equivalent to 24 hours. So from this one, okay, we can now solve for y of t. This one, so we have here y of t. Using this given equation, 8,000. Okay? E to the power of, okay, we have here k. The value of k is 0.2798 times t. But our t here is 24. So we can now have y of 24 is equivalent to 8,000 times e to the power of 0.2798 multiplied by 24 hours. Okay? So using our scientific calculator, we can now have y of 24, or in one day, there are how many cells present? We have 6,598,000. Okay? And 790 cells. Okay, in one day. So imagine how many bacteria in one day? 6 million. Okay? So using our constant value, which is 0.2798. So this will be the solution for the differential for this problem, which is the application for the differential equation. Okay? So in one day there are 6,598,790 cells in one day.